Hello dear students, welcome back to your physics class. On today's lesson, we are going to talk about the rotational kinetic energy. If you remember in a previous lesson, we talked about the conservation of angular momentum. The angular momentum is conserved in the absence of the torque. When the net torque acting on the object is zero, this object has a conservation of angular momentum, such as the ice skaters can control his or her angular speed. Okay? In the case of extending his arm or legs away from his body, in that case, the angular speed decreases, but the moment of inertia increases, and the angular momentum stay unchanged. Okay? Today's lesson, we will talk about the kinetic energy. If you remember in grade 11, you have learned about translational or linear kinetic energy, okay, which is equal to 1/2 mv squared. Linear kinetic energy or translational kinetic energy depends on mass and square velocity of the object. But rotational kinetic energy is completely different with the translational kinetic energy. And instead of mass, in rotational kinetic energy, we have moment of inertia, and then instead of velocity, we have angular speed or angular velocity. Okay? Translational kinetic energy of an object due to its translational motion. Measured in what? Joule, and depends on the object's mass and the square velocity, as you can see in this equation. Okay, but rotational kinetic energy, so this is translational kinetic energy, okay, is equal to 1/2 mv squared. But rotational kinetic energy is equal to 1/2. Okay, what is the rotational analog of mass? Is moment of inertia. Rotational analog of mass is what? Moment of inertia. So what about the rotational analog for the velocity or speed? Is angular speed. Okay? So this is the rotational kinetic energy, which is equal to 1/2 I times omega squared. I is moment of inertia and omega is angular speed, and also measured in joule. Okay? So the relationship between rotational kinetic energy and the angular momentum. So we can represent rotational kinetic energy like that. Okay, 1/2 I times. And instead of omega squared, if you remember, in the angular momentum, L is equal to what? I omega. Okay, so what about omega is equal to what? Omega is equal to L over I. Okay, so omega squared is equal to what? Omega times omega. And instead this omega squared, you can write down omega times omega. Okay, so if you remember in a previous lesson about the angular momentum, L is equal to what? I omega. Okay, so instead of this I omega, we can write down 1/2, and instead of I times omega, we are going to write what? Angular momentum, L times omega. Okay, so what is the relation between these two equations? Also, what is the difference between these two equations? In this equation, if you see, rotational kinetic energy is directly proportional to the square of angular speed. Okay, rotational kinetic energy here is directly proportional to what? To the square of angular speed. But in this equation, rotational kinetic energy is directly proportional to the angular speed without square. So in this equation, angular momentum is not conserved. Okay, when does rotational kinetic energy is directly proportional to the square of angular speed? When the object's angular momentum is not conserved, such as a sailing fan. For example, when the sailing fan's angular speed increases by factor 2, in that case, rotational kinetic energy increases by factor 4. So in that case, for the objects whose moment of inertia doesn't change during rotating, or for the objects that its angular momentum is not conserved, such as a rigid body during rotating, like sailing fan or merry-go, in these examples, the angular momentum is not conserved. When the angular momentum is not conserved, The relation between rotational kinetic energy and angular speed is directly proportional with the square. Be careful. But for the object whose angular momentum changes during rotating, such as ice skaters, in that case, the angular momentum is conserved. When moment of inertia increase, angular speed decrease. When the moment of inertia decrease, angular speed increase. But its angular momentum doesn't change. When the angular momentum is conserved, in that case, rotational kinetic energy directly proportional to the angular speed without square. Pay attention, please. Be careful. Without square. Once again, when does rotational kinetic energy is directly proportional to the angular speed without square? When the object's angular momentum is conserved. So, when does rotational kinetic energy is directly proportional to the square of the angular speed? When the object's angular momentum is not conserved, such as a sailing fan, as I mentioned. Okay? So, this is very important. Please pay attention. So, kinetic energy is equal to what? 1 over 2L times omega when the angular momentum is conserved. Now, what is total kinetic energy? What is total kinetic energy? The words of total, it is that the summation or the sum of all kinetic energy. For example, if we have inclined surface, okay? So this is, assume that this is rough surface, okay? This is rough surface. It has a friction, okay? If you release this bowling ball on this rough surface inclined, in that case, the object is start rolling down, okay? Until reaches the bottom of the incline, okay? So, what is the type of the motion of this bowling ball? So, it is rotational motion or translational motion? Has both. This object, when we release a bowling ball at the top of the incline, on a rough surface incline, in that case, the bowling ball has both types of motion, rotational motion and translational motion. Because the object rotates around itself, it has rotational motion, and the object's center of mass changes continuously. That is why the object also has translational motion. Okay? So, what about the kinetic energy? Which type of kinetic energy do we have? So, we have two different types of kinetic energy here. Translational kinetic energy and rotational kinetic energy. At first, the object has only gravitational potential energy. But this gravitational potential energy is converted to what? To kinetic energy. Which kinetic energy? Translation or rotation? Both of them. So that is why we have to write down what? Total kinetic energy. So in that case, all gravitational potential energy is converted to what? To total kinetic energy. So total kinetic energy is equal to what? The sum of translational kinetic energy and rotational kinetic energy. So what do you mean by total kinetic energy? Is the sum of translational kinetic energy and rotational kinetic energy measured in joule. Okay? Kinetic energy total 1 over 2 mv squared plus 1 over 2 I omega squared. Kinetic energy is a scalar quantity. It's always positive. Okay? If angular momentum is conserved, then both angular speed and moment of inertia changes together. So in that case, write down on your pamphlet, please. If angular momentum is conserved, in that case, angular speed and moment of inertia changes together. So, kinetic energy, rotational kinetic energy is equal to what? 1 over 2L omega squared. Okay? When the moment of inertia and angular speed changes together. But if angular momentum is not conserved, then angular speed changes, but moment of inertia doesn't change, so there's a sailing fan. In that case, kinetic energy rotation is equal to what? 1 over 2 I omega squared. In this case, angular momentum is not conserved. Okay? If you remember in chapter 1, there is a relation between linear quantity and angular quantity. tangential speed is equal to what? Omega times r. Okay? So what about omega? Rearrange equation Vt over r. Okay? If omega is square, Vt square over r square. Now, gravitational potential energy. So you studied in grade 11. What is gravitational potential energy? Is the stored energy of an object due to its motion or position? Due to its position. For example, when an object is placed at some height, in that case, the object has potential energy. So the potential energy depends on mass, gravity, and height. Okay, as you can see in this picture, in this figure, okay, the ball catched by this girl. This ball has potential energy. Okay, why? Because it has height and also it has mass and gravity already present in that case. So the potential energy increases by increasing mass, increases by increasing height. Okay. Mechanical energy. What is mechanical energy? There is a difference between total kinetic energy and mechanical energy. Mechanical energy, its definition is very important and it has been brought in the Wasario exam. Please pay attention. Is the sum of all the types of kinetic energy and potential energy. The sum of what? All types of kinetic energy. Why he said all types of kinetic energy? Because we have two different types of kinetic energy, rotation and kinetic energy. And the potential energy. Mechanical energy is equal to kinetic energy translation plus kinetic energy rotation plus gravitational potential energy. Okay, so here we have some important tips and notes about the rotational kinetic energy. When an object rolls down at the top of the inclined surface without slipping, rough surface, gravitational potential energy is converted to total kinetic energy. Okay, when does gravitational potential energy is equal to total kinetic energy? When the object is rolling down or rolls down at the top of the incline without slipping. It means that rough surface. But in the case of when the object is rolls down on a smooth surface, there is no rotational kinetic energy. The object has only translational kinetic energy. For the smooth surface, when we release an object at some height of an incline, in that case, only the potential energy converted to translational kinetic energy. Joule, it is the equivalent unit of joule, Newton meter, kilogram meter square per second square. If several similar objects, same moment of inertia. What do you mean by similar object? Same moment of inertia. All objects, they have the same moment of inertia. Roll down at the top of the inclined surface, but differ in mass and radius. They will reach the bottom of the incline with the same velocity, because the velocity of the object at the bottom of the incline does not depend on mass and radius. And instead, it depends on the gravity and height and the shape of object. Okay? For example, the speed of the speed of the ring or thin hoop at the bottom of the incline is equal to what? Is equal to gh. Okay? The speed of solid, this is for ring. The speed of solid speed is equal to what? Is equal to 10/7 gh. Okay? At the bottom of the incline, this object has a speed. How can we determine the speed of the object? By using this equation. So, for each shape had its own tangential speed at the bottom of the incline. The velocity at the bottom of the incline for the solid sphere is equal to 10/7 gh. What does the velocity of the object at the bottom of the incline of the rough surface depend on? It depends on height, gravity, and the shape of object. As you can see in these two equations, we have one here, but we have 10/7 here. Okay? Now I'm going to prove how did we get this equation. For example, for the ring. For ring or the thin hoop, V is equal to what? This is the velocity of the object at the end of the incline or at the bottom of the incline. The velocity of the ring is equal to what? G times GH. Okay? How did we get this equation? Now I'm going to prove. Okay? Listen to me, please. In that case, for example, we have an incline and we have a ring. What is the shape of the object? Is a ring. Okay? what is the velocity at the bottom of the incline? Okay, as you can see in this figure, what we have at first, which type of energy stored here? Gravitational potential energy. This is rough surface, be careful. This is rough surface, this is not smooth. Okay, in that case, all potential in gravitational potential energy is converted to what? Total kinetic energy. Okay, so gravitational potential energy is equal to what? Is equal to mgh. Kinetic energy total is equal to what? Is equal to translational kinetic energy plus rotational kinetic energy. Bring down this mgh. Translational kinetic energy is equal to what? 1 over 2 mv squared plus kinetic energy 1 over 2 I omega squared. Okay, mgh is equal to 1 over 2 mv squared plus 1 over 2. Instead of this moment of inertia, the moment of inertia for ring is equal to what? Is equal to mr squared. Instead of this moment of inertia, this is for ring. Write down what? mr squared. Time is, instead of omega squared, write down what? V squared over r squared. Why? Because omega is equal to V over r. What about omega squared? V squared over r squared. R squared with r squared cancel. What does remain? mgh plus 1 over 2 mv squared plus 1 over 2. What does remain here? mv squared. Okay, 1 over 2 mv squared plus 1 over 2 mv squared, because they have the same term, we can add up this two number. Okay, mgh is equal to 1 mv squared. Okay, mass with mass cancel. What does remain? V squared is equal to gh. Take the square root, this square will be removed, and what does remain? gh. What is this? This is the velocity or final velocity for the ring when it is rolling down at this incline. Okay, so this is the velocity at the bottom of the incline of ring. Okay, so that is why if you have many or some of similar objects, it is that they have the same shape. For example, if you have several rings, in that case, if you're rolling down from this incline with a different mass and different radius, in that case, both objects reach at the bottom of the incline, because the velocity of the ring or the velocity of the different shape does not depending on mass and radius. And instead, depends on the height of the incline and the shape of the object. But if several different shapes, different in moment of inertia, are rolled down at the top of the incline, but equal in radius and mass in the object, with the lower moment of inertia reaches the bottom of the incline, because moment of inertia is inversely proportional to the angular speed. So the mechanical energy is conserved. Initial mechanical energy is equal to final mechanical energy. This is for the rough surface. But for the smooth surface, okay, for the smooth surface, velocity at the bottom of the incline is always equal to 2 radical 2gh for all shapes. Why? Because, for example, if you have many different shapes like solid sphere, ring, or disc, or hollow sphere, okay, in that case, all objects, they have the same velocity. Why? Because in the case of smooth surface, so our surface here is smooth. What do we mean by smooth surface? It means that there is no friction. In the case where there is no frictional force, in that case the object does not rotate. Okay, so instead the object is moving with the translational motion only. Okay, so which type of kinetic energy do we have here? Only translational kinetic energy. So in this case, all the gravitational potential energy is converted to what? Total kinetic energy or translational kinetic energy? Only translational kinetic energy. Why? Because the surface of the incline is a smooth surface. In a smooth surface, rotational kinetic energy is zero. Why? Because the object does not rotating. Its angular speed is zero. Okay? So gravitational potential energy is equal to mgh, and translational kinetic energy is equal to mv squared. Mass with mass cancel. Okay? V squared is equal to what? Is equal to 2 times gh. So take the square root. V is equal to what? 2 radical 2 gh. This is for which shape? For all shapes. Okay? For all shapes on a smooth surface. Okay? So, which object has more velocity at the bottom of the incline? When the object released on a smooth surface or rough surface? Absolutely on the smooth surface. Why? Because on the smooth surface, there is no friction. Okay? All the potential energy is converted to what? Translational kinetic energy. So which of the following has more velocity at the bottom of the incline? Smooth surface or rough surface? Absolutely the smooth surface. Okay? So here we have some velocity, final velocity at the bottom of the incline for some shapes. Okay? So you can prove one by one. Okay? Final velocity for the ring, wheel, bicycle on a rough surface. Be careful. So these are for what? For the rough surface. Final velocity for the solid cylinder, disc, pulley, merry-go, coin is equal to 4/3 gh. Radical 4/3 gh. For the hollow ball, basketball, football ball, final velocity is equal to radical 6/5 gh, and the solid sphere is equal to radical 10/7 gh. The following equation can be used when the angular speed is given or unknown for an object that rolls down an inclined surface. So V final is equal to R omega, and omega is equal to V over R. If an object slips down on a smooth surface, no friction without rotating, in that case V final is equal to what? Is equal to 2 gh. When object slipping, rotating, not rotating, sorry. For all shapes. Okay? For all shapes. So in that case, gravitational potential energy is equal to translational kinetic energy. Okay? The velocity of an object that's rolling down on a rough surface does not depend on mass and radius, as I mentioned. Okay? Its velocity is equal to the factor times gh. This factor, the number of moment of inertia. Okay? But for the smooth surface, velocity is equal to radical 2 gh. Okay? In the question, sometimes when the height is not given, okay, this is inclined surface, this is angle, this is height, and this is d. Okay? So to find, for example, the final velocity for the ball, this is solid sphere, assume that for the solid sphere. For the solid sphere is equal to 10/7 gh. Okay? It depends on height and it is factor. Okay? But if the height is not given in the question, and instead of height d, the distance of the incline and the angle is given, according Pythagorean theorem, sine theta is equal to what? Opposite over hypotenuse, h over d. If you have angle and distance of the incline, you can find out the height of the incline, which is equal to what? D sine theta. Okay? Because some questions, the height is not given in the question. You have to try to find height, but instead of height, the distance and the theta must be given. Okay? And if the adjacent is given of the incline, also you can find out height by using cosine. Okay? So sometimes this distance is not given in the question, and the question asks us to find the distance of the incline. Also, you can find out d is equal to h over sine theta, or d is equal to what? The for kinematic equation at constant acceleration can be used, is equal to v initial plus v final times delta t. Okay, in these two ways, you can find out the distance of the incline. By using, when height is given with the angle, you can find out the distance, which is equal to the hypotenuse according to Pythagorean theorem. And also when the height is not given or the angle is not given, instead of height and the angle, V initial and V final and time must be given in the question. And also this equation it's very important to find what? The time. The time that takes for the object that releasing from an incline. For example, when the question asks how long does it take for the solid sphere releasing or moving from an incline to the bottom of the incline? Okay? So it is very important, please pay attention. Now we have some ratio. Okay, so you can prove one by one. What is the ratio of rotational kinetic energy to total kinetic energy? And total kinetic energy to rotational kinetic energy for ring, rotational kinetic energy to total kinetic energy is equal to 1 over 2. So you can prove it, and it's very easy. Find or prove that rotational kinetic energy to total kinetic energy, Y is equal to 1 over 2. Listen to me, please. Rotational kinetic for ring, for what? For ring. The shape must be mentioned, okay? Rotational kinetic energy for ring is equal to 1 over 2 I omega squared. Total kinetic energy is equal to the summation of translational kinetic energy plus rotational kinetic energy, okay? 1 over 2 times moment of inertia for ring is equal to what? M R squared times V squared over R squared, because omega is equal to V over R squared, okay? R with R cancel, over 1 over 2 mv squared plus the same thing, 1 over 2 I for ring is equal to m R squared, omega squared is equal to V squared over R squared. R with R cancel. What is remain at the denominator? 1 over 2 mv squared. At the denominator, 1 over 2 mv squared plus 1 over 2 mv squared. Okay? This is equal to 1 over 2 mv squared over what? 1 over 2 plus 1 over 2 is equal to 1. mv squared. mv squared cancel. What is remain? 1 over 2 divided by 2 is, if they divide by 1, is equal to what? 1 over 2. So this is the ratio of rotational kinetic energy to total kinetic energy is equal to 1 over 2. So you can do it one by one for all shapes. It is very easy, and I suggest for you, don't memorize, please. Okay? So you have to prove one by one, and it is very important. And also we have this fast way to find out the ratio of the kinetic energy. Okay? So that's all for today. Thank you for listening. Inshallah, in the next lesson we will continue to solve and explain the others about rotational kinetic energy. Keep up your best doing. See you again, inshallah.